Before the tallest building in the world was even finished, engineers were already calculating how far its enormous foundation could settle into the earth. As they modeled the unprecedented weight of the tower, several design analyses produced estimated settlement figures, ranging from 45 to 62 millimeters. To a normal person, the idea of a mega-tall skyscraper sinking roughly 2 inches into the ground sounds like a catastrophic failure. You look at a structure that massive and assume any downward movement is a sign of impending collapse. But in the strict reality of structural engineering, those specific measurement numbers were considered acceptable. They were well within the boundaries of the design analysis for the foundation. The massive weight of concrete and steel was always going to interact with the earth. The engineering source explicitly notes that this level of movement was anticipated and planned for. Because, as counterintuitive as it sounds, 62 millimeters was not the movement engineers had the most reason to control. If the overall downward movement was acceptable, there was another physical threat waiting beneath the surface. A threat that changes how you understand the world's most famous skyline. The immediate instinct is to assume a properly engineered skyscraper should never move at all. You look at a massive structure dominating the skyline and expect it to behave like an object permanently bolted to an immovable planet. But physics does not allow for a zero reaction when you place an unprecedented vertical load onto the ground. When hundreds of thousands of tons of concrete and steel press down, the material underneath has to respond. Some deformation of the ground is simply going to occur. You cannot build something this incredibly massive and expect the earth to simply ignore the pressure. The ground is not an indestructible block of solid steel. It is a complex physical system that compresses when subjected to immense continuous forces. Think of it as a massive physical interaction between the structure and the planet. A small load produces a tiny, almost invisible response from the earth. But an enormous skyscraper load means the foundation and the ground must interact constantly and dynamically. If you accept that the ground is going to compress, the obvious solution seems incredibly simple. You just drive giant piles deep enough into the earth to freeze everything in place and stop the movement entirely. You force the ground to become rigid and unyielding by pinning the building to it. You push through the soft layers until you hit something solid enough to hold the weight without flinching. Except the foundation of the Burj Khalifa was not designed around the assumption of zero movement. The engineers knew they could not simply lock the building into a perfectly static state, which raises a strange and critical question for the entire structural system. If the deep foundation piles are not there to completely eliminate settlement, what are they actually doing down there? Before we can answer what those piles are doing, we have to look at what the tallest building in the world is actually sitting on. The site was investigated extensively before construction began to understand the exact geological conditions. Engineers drilled deep boreholes to characterize the natural subsurface layers waiting below the proposed tower. And they found exactly what you would expect in this specific region of the world. The material beneath the tower is not just one uniform block of loose desert sand. Below the near-surface deposits, the earth is horizontally stratified into distinct geological bands. There are different layers of carbonate soil and rock stacked on top of one another like a geological ledger. As you go deeper, the material properties change again, eventually reaching deeper, weaker rock formations. Every single one of these horizontal layers has its own unique mechanical properties. They respond to intense downward pressure differently. They compress at completely different rates when subjected to the exact same amount of weight. They hold vertical loads differently depending on their exact composition and depth below the surface. The underground is a highly variable and complex environment, and that geological reality creates a problem much more important than whether the entire tower simply moves downward. Imagine a scenario where the entire foundation of a massive skyscraper moves downward by the exact same amount at the exact same time. The building settles into the earth, but the massive structural core remains perfectly upright and straight. The floors remain completely level, and the center of gravity does not shift. The structure simply sits a fraction of an inch lower than it did before the immense load was applied. This uniform downward movement is a highly manageable engineering reality. Now imagine a second, vastly different physical scenario. One part of the massive foundation moves just a little bit further into the earth than the other side. The downward force pushes through a slightly weaker layer of rock on one edge, causing a localized drop. This is not just a building moving down into the earth. This is a building distorting under its own enormous weight. The engineering term for this specific failure mode is differential settlement, and it is the true nightmare of any structural engineer working on a mega project. The foundation design for the Burj Khalifa explicitly considered both overall settlement and differential settlement, because if uneven foundation movement became sufficiently large, the consequences would go far beyond a few millimeters of depth. Different parts of the massive structure would begin to change their relative positions. The incredible forces moving through the concrete and steel would be redistributed in ways the architects never intended. You would start to see severe serviceability problems multiplying throughout the entire tower. Elevator shafts could become misaligned, causing massive operational failures for the transit system. Facade panels could experience extreme stress, leading to cracked glass and compromised weather seals. And eventually, the uneven movement could lead to potentially serious structural consequences for the entire core. The important question was never simply how many millimeters the tower might move downward into the ground. The real threat was how differently separate parts of an enormous foundation might move relative to one another. To understand how the Burj Khalifa Foundation manages that differential settlement, you have to look at what is actually holding the building up. When you peel back the concrete of the plaza, you do not just see a flat slab resting on the dirt. You see an incredibly complex, interconnected structural system. The engineering source describes a massive pile-supported raft foundation. It begins with a solid reinforced concrete raft, approximately 3.7 meters thick. That is roughly 12 feet of solid, continuous concrete just to transfer the massive weight from the tower above. But that enormous raft is not sitting on the ground alone. It is supported by a subterranean forest of massive tower piles. Each concrete pile is approximately 1.5 meters in diameter, and they do not just go down a few feet into the sand. They extend roughly 50 meters beneath the base of the massive concrete raft. When you hear those incredible dimensions, it is easy to think the problem is permanently solved. With a 3.7-meter raft and piles plunging nearly 50 meters into the earth, you might assume engineers simply turned the ground into an immovable block. But those massive piles do not magically turn the layered earth into solid, unyielding steel. The tower, the massive raft, the deep piles, the ground, and the deeper geological layers all function together as a unified system. The vertical weight of the skyscraper travels down into the concrete raft. The raft distributes that immense load to the piles and directly into the soil beneath it. The piles transfer their share of the load deeper into the earth, through friction along their sides and pressure at their base. And this is where a critical factual point from the original engineering paper changes the entire narrative. The authors concluded that the foundation design was governed primarily by tolerable settlement rather than simply overall allowable bearing capacity. In ordinary language holding, the weight was only part of the complex problem. Controlling how much the building moved and specifically controlling how evenly it moved mattered just as much. The piles were not designed to stop the earth from compressing entirely. They were designed to control the compression so the movement remained within safe, tolerable limits. But predicting that movement on a complex computer model is one thing. How do you trust that prediction beneath a tower no one had ever built before? You do not just trust the computer model, you force the physical ground to prove it. Long before the massive 3.7-meter raft was poured, engineers had to know exactly how the piles and the earth would interact. They moved away from theoretical physics and began a massive physical testing program on site. They brought in heavy hydraulic testing systems capable of generating immense pressure. They installed sensitive strain gauges deep underground to measure the exact internal deformation. They built massive reaction structures on the surface to push back against the forces they were generating, and they began pushing real concrete piles to their absolute physical limits while recording every millimeter of movement. The engineering source reports static tests on 7 trial piles before foundation construction even began. Then they ran static tests on 8 more works piles during the actual foundation construction phase. They did not just test for simple vertical downward weight. They ran dynamic testing and integrity testing to understand every possible failure mode. They tested different pile lengths to see exactly where the friction was most effective in the specific soil. They tested different shaft treatments to optimize the mechanical grip between the concrete and the rock. They tested uplift forces to simulate what happens if a pile is pulled out of the ground. They tested lateral loading to see how the pile handled horizontal pressure from shifting earth. The broader testing program included extreme loads reaching approximately 64 meganewtons. That is an immense amount of physical force being driven into a single point in the earth just to see how the ground responds. The engineers were not merely trusting a theoretical model in an air-conditioned office. They were forcing real concrete piles to reveal their true behavior under extreme pressure. They were literally testing the limits of the earth before trusting it with the world's tallest building. The piles survived the intense physical questions coming from below. But the Burj Khalifa would also be attacked from above. A megatall skyscraper is not simply a stationary vertical weight pushing straight down into the ground forever. It is a massive vertical sail standing in the wind, and that wind produces constantly changing structural loads on the entire building. When a storm hits Dubai, the wind pushes violently against the sheer vertical size of the Burj Khalifa. The tower conceptually sways in response to the aerodynamic pressure. As it does, the incredible loads shift rapidly through the entire structure. They move down the core, they travel through the structural walls, and they hit the foundation unevenly. When the wind blows hard against one side, the deep piles on the opposite side experience a massive increase in downward pressure. When the wind shifts direction, the massive loads immediately switch sides. This means the foundation and the deep piles do not just experience a constant steady weight. They experience highly varying demand throughout any weather event. They are repeatedly loaded and unloaded in rapid succession. The foundation study explicitly investigated these cyclic loading effects associated with wind loading. The engineers needed to know what happens when giant pile loads change again and again over the lifespan of the building. Their analyses suggested that cyclic pile load variations for the case studied would not exceed roughly plus or minus 10 meganewtons, and the authors concluded that the expected cyclic effect was unlikely to significantly degrade pile capacity or settlement performance under those specific design conditions. The foundation was mathematically and physically prepared to handle the shifting weight of the wind without failing. Even if the structural models and the physical tests looked good, how could engineers know Dubai skyscrapers would actually behave that way over time? The Burj Khalifa was not the first time Dubai engineers had to calculate how a massive structure would settle into the deep soils. The city had already learned from other immense towers. If you look away from the Burj Khalifa, you find the Emirates Towers. This is a completely different Dubai landmark built years earlier, but it provided a crucial engineering lesson for everything that followed in the city. A published engineering study of the Emirates Twin Towers describes piled raft foundations built on deep calcareous soils and rocks. And crucially, the study directly compares the predicted settlement behavior with the observed settlement behavior of the finished structures. Settlement prediction was not unique to one bizarre, impossible building in the center of the city. It was an ongoing applied science across all of Dubai. Experience from the nearby Emirates project was explicitly used during independent verification work for the Burj Khalifa foundation model. The engineers had real-world physical data from a massive twin tower project built on similar deep soils in the exact same geographic region. They knew exactly how those specific foundations had settled compared to their original computer models. They knew where the predictions were overly aggressive and where they were safely conservative. The Burj Khalifa was not a blind engineering experiment operating in a vacuum. It was a gigantic extension of structural lessons Dubai engineers had already been learning for years on other massive projects. They had the highly sophisticated computer models. They had the extensive trial pile data from the exact site. They had the advanced aerodynamic wind analysis. And they had the historical observational data from the Emirates towers. But older towers and sophisticated computer models still could not answer one final critical question. What would the Burj Khalifa itself actually do once the real building load finally arrived? The massive 3.7-meter concrete raft was finally poured, and the immense steel and glass structure began to rise into the sky. And as the unprecedented weight of the Burj Khalifa slowly transferred into the earth, the engineers were watching closely. They had installed highly precision monitoring points to track exactly what the foundation was doing at all times. They had their complex computer models and their perfectly predicted ranges of movement. Now they needed to see what the ground would actually do under real structural pressure. The settlement of the tower raft was carefully monitored through a dense network of instruments throughout the entire construction process. By March of 2007, the tower had reached a critical phase of its physical ascent. At that specific reporting date, engineers estimated that roughly 75% of the dead load was finally acting on the foundation. Hundreds of thousands of tons were heavily pressing down on the piles and the subterranean rock layers. Additional dead and live load still remained to be applied as the tower climbed higher and prepared for human occupancy. But this was the specific moment the theoretical numbers finally met physical reality. The deep monitoring equipment delivered the undeniable results. The measured settlement at that reported stage of construction was considerably below the original design predictions. The authors of the engineering study noted that the settlement measured during construction was consistent with their theories but significantly smaller than predicted. They concluded that the performance of the piled raft foundation system had exceeded expectations up to that specific point. They had deliberately built massive conservative margins into their calculations to allow safe room for the earth to move. And reality, at that reported construction stage, was behaving much better than those strict conservative limits required. So if the entire foundation system was so heavily engineered and performed so well in reality, why use a phrase like designed to sink? Because the true engineering victory here requires a complete shift in how you view the physical world. The foundation of the Burj Khalifa was not designed to fail. It was specifically designed for tolerable settlement. The engineers knew they could not force the earth to remain perfectly motionless under the tallest building in human history. They were designing a massive structural system while fully acknowledging that some downward settlement was a physical certainty. The primary engineering source specifically says the foundation design was governed primarily by tolerable settlement limits. And its various complex analysis methods produced a predicted maximum tower settlement ranging around 45 to 62 millimeters, which was considered entirely acceptable. The real engineering victory is not forcing the ground to remain perfectly motionless. It is understanding the complex geology, testing the raw materials, predicting the physical response, and perfectly distributing the immense load. Most importantly, it is entirely controlling the differential movement. Uniform downward movement can be completely manageable for the structure. Uncontrolled, uneven movement is the ultimate structural nightmare. By perfectly predicting and safely managing the settlement, they allowed the massive building to find its physical equilibrium safely. The highly skilled engineers for the Burj Khalifa could rely heavily on deep geological history. They had the ability to drill deep boreholes and carefully characterize natural subsurface layers that had been sitting there for millions of years. They could build highly accurate models, test real concrete piles, and monitor the settlement of perfectly solid natural ground. They were working with a stable earth that had already been heavily compressed by infinite time and intense pressure. But as you look away from the stable center of Dubai and move out toward the vast coastline, the rules of engineering completely change. You do not just see massive towers built on stable natural desert rock. You see sweeping massive developments, vast artificial islands, and luxury skyscrapers sitting heavily on freshly reclaimed land. Dubai boldly builds major global landmarks on soft land created entirely by humans. And that specific ambition introduces an entirely different set of complex geotechnical threats. If accurately predicting the settlement of natural layered rock requires massive physical testing and deep computer models, the physics become vastly more complicated in the open ocean. What exactly happens when you want to put enormous buildings on deep ground that did not even physically exist a few years before? The incredible story of the Burj Khalifa Foundation perfectly proves that true engineering is not simply about fighting gravity into a total standstill. It is about understanding exactly how much the Earth will naturally yield and precisely designing a structure that moves safely with it. They accurately predicted the settlement, they aggressively tested the physical limits, and they completely controlled the nightmare of uneven differential movement. Uniform settlement was entirely anticipated and perfectly planned for. Differential settlement was the real enemy that had to be defeated. And by fully mastering that critical distinction, they successfully built the tallest freestanding structure in human history. But perfectly solving stable natural ground is only half the engineering story of Dubai. This video is for educational and analytical purposes only and relies heavily on available structural engineering reports regarding early construction stages. It is not intended as professional structural or direct geotechnical engineering advice. If you want to see exactly how Dubai solves the totally impossible engineering problems on its massive artificial islands, make sure to heavily subscribe. We will immediately see you in the very next investigation.